So in a minute, I will stop the sharing and I will give the sharing opportunity to everybody. And of course, to you in particular, Levon. Okay, you should use it. This is the point.
Okay.
I shall open my own timetable.
Yes. I think, Levon, you can now share your screen.
Okay. Should I, or should I wait for you? Actually, it's 1 minute, so maybe I'll just.
So Alexei is now the chairman.
Yeah. Okay, yes, Levon, open your presentation, please.
Okay, can you see?
Yeah.
Okay, yes, indeed.
Oh, and just tell us which mountains are these?
So this is basically close to Vancouver.
Vancouver.
And the water is an inlet of the Pacific Ocean that curves into the mountain.
Yes,
and
indeed.
the buildings.
I see now the form of them. Okay, so let's begin. Let's begin our session. Our session on dark energy. Okay, we have rather small, I would even say intimate audience, but certainly all persons are experts in the field. So okay, so the first talk will be by Dr. Leon Pogosyan, Cosmological Reconstruction of Gravity. Please.
Okay. Thank you, Alexei and David and everyone for coming to here to listen. This is work in collaboration with a group of people. Most of them are my longtime collaborators. And you all being experts makes my job a bit easier, but also I'm aware that there's going to be a recording and some people will be watching it in a recorded form. So I'll just go through the background as well. So my talk is about what we can learn from cosmology about gravity. And when we say gravity, we mean general relativity. And there are good reasons to keep an open mind about general relativity, even though it is one of the best tested theories we've ever had, especially when it comes to its application to cosmology. And this is a list of reasons that anyone here would probably put down as well. And for me, the last one, the opportunity to test general relativity on cosmological scales is quite important because we have not had that opportunity until recently. So it's just starting to become available with better surveys, with more tomographic ability of the surveys to test validity of Einstein's laws at many redshifts. And of course, the topic of tensions has received a lot of attention recently, namely the H0 tension and some others. So what can we actually learn from cosmology? We could look at the expansion history of the universe using various traces, various indicators like the luminosity distances and baryon acoustic oscillations. We could also check if the growth of large-scale structures proceeds as expected in lambda CDM and general relativity. We could also design special triggers, frameworks that would tell us if they are signatures of some new physics, like new interactions or breaking of the equivalence principle. And those two things often go together. And then if we are interested in alternative theories, in extending Einstein's theory, then we could learn which of these alternative theories are allowed. So this field, thanks to many people in the audience, has matured a lot over the past 15, 20 years. So at the beginning, they were just, the beginning coincided with the discovery of cosmic acceleration. And we had theories like DGP and F of R, and now we have a more complete understanding of scalar tensor theories in terms of the broad class of scalar tensor theories such as Horndeski and beyond Horndeski. And they are effective frameworks that allow to efficiently describe the evolution of background and perturbations in this type of theories. And they are sophisticated numerical implementations of this in Boltzmann codes that allow for very simple evaluation of predictions of these theories and comparing them to observations. In parallel, there is another approach, which is more phenomenological, not based on theory, but simply based on what data can constrain the best in terms of these parameters mu and sigma, which I'll introduce shortly, which also is implemented numerically. And there is a mapping between these phenomenological parameters and Horndeski theories and the EFT version of it. So this ABC, these three different approaches, are highly complementary. The first two are specific to scalar field models. C is closer to what data is constrained, but we could use A and B to inform our studies of C. And so in this work that I'll present, what we have done is reconstructed mu and sigma, but with the help of a prior that we derived from Horndeski theories using this EFT framework. And we, as you'll see, I'll show results with and without this prior. So it's also interesting to compare. So let's start with the background, just to define my parameters. I'm going to parameterize departures from lambda CDM in terms of this function x. And the idea is that you could have a modified gravity in which the Friedmann equation looks nothing like the usual Friedmann equation. But whatever new terms I have, I'm going to rewrite my equation in this form. So all the modified gravity effects, interactions, etc., I could shove into one function called x of a. So it's everything that's not minimally coupled matter or radiation, and call it effective dark energy. And by construction, this effective dark energy is conserved. Now, it's more correct to work directly with this function x as opposed to some effective equation of state of it, w, because we know that in scalar tensor theories, w can easily pass through zero and change its sign, in which case, rho effective dark energy density can pass through zero and change its sign, so W becomes singular. And so when you parameterize things in terms of W, you can bias your results when studying modified gravities. And perturbations, as I mentioned, we're going to describe using these functions mu and sigma. So the idea is that we assume that baryons and cold dark matter are coupled to some modified gravity scalar field in the same way. So they follow the geodesics of the same metric. In other words, there is a Jordan frame that's the same for baryons and CDM, and we work in that frame. So in that frame, all the matter is conserved. And we modify Einstein's equations for linear perturbations by introducing these phenomenological functions mu and sigma, and gamma is related to them. It can be simply derived from mu and sigma. You only need to define two. Any of these two defines the third one. And these things are often referred to as G meta and G light. And the reason for it is the definition. The first one, mu, relates the meta perturbation to the Newtonian gravitational potential, while the second relates the meta perturbation to the Weyl potential, which determines the weak lensing effects. And we're looking for something like these two G's being unequal, or phi, which is the curvature perturbation, not being equal to the Newtonian potential, as a smoking gun of modified gravity. So if you now look at the theoretical predictions for these functions, you can only do it by adopting the so-called quasi-static approximation. And that involves going on sub-horizon scales and ignoring any dynamics of your scalar field and the metric that's not associated with just growth of meta perturbation. So any additional dynamics like oscillatory behavior of your scalar field would be ignored. And these expressions contain some functions of time, which are listed here, the 5 of them in this expression, which can be expressed in terms of functions appearing in the Horndeski Lagrangian. I'm not going to write them here. So in particular, this CT is the speed of tensor modes or gravitational waves, which we know has to be 1 today, but in principle, on purely with, if you have a completely open mind, it could be different at earlier times. Now, in many of the models that have been studies, like specific examples of Horndeski, like chameleon type models, F of R, symmetrons, Galileans, you're likely to be in one of the 2 limits. So if you are in models which have this Weinstein type screening, this scale M, which is effectively the Compton wavelength of your scalar field, is likely to be comparable to the horizon scale. So all the modes that you study in large scale surveys are likely to be below that. So there, when you actually do your measurements, you're likely to be at K much greater than M. And in models of chameleon type, this M is constrained to be less than 1 megaparsec. So on linear scales, your large scale surveys would likely be always above that. So with that in mind, we can look at the limits and see what we can learn from them. So in a small K limit, which is the large scales, these expressions reduce a lot. And you see that, for example, any signature of gamma, which is the gravitational slip, being not zero, would indicate non-trivial speed of gravitational wave. So the only way gamma can be non-zero, non-zero, not equal 1 in Horndeski, is if CT is not equal to 1. Now, and in the other limit, you can have additional effects which come from the fifth force type interactions. And you can learn a lot from this. So if you measure these functions, let's say they are not equal to 1, it's not just that you ruled out lambda CDM. You can actually rule out a lot of the Horndeski theories. For example, if you measure gamma greater than 1, that rules out all of Brans-Dicke type theories, because gamma is strictly less than or equal to 1 in Brans-Dicke. When by Brans-Dicke, I mean all theories which have a canonical kinetic energy term for the scalar field. So if you measure gamma not equal to 1 with some significance, it can only be something which has a Galilean type kinetic energy terms. And also, Alessandro Silvestri and I found by analytical examination of these functions that this condition on the bottom, that sigma minus 1 times mu minus 1 has to be less than, it has to be greater than or equal to 0. In other words, if sigma is greater than 1, then mu also needs to be greater than 1. And if sigma is less than 1, then mu also needs to be less than 1. So if you find a violation of this condition, it doesn't rule out there is a way to design a Horndeski theory. But okay, 5 minutes, very good. So we reconstruct this using, we reconstruct these 3 functions, omega x, mu, and sigma, together using this following approach. We parameterize them using 11 nodes in redshift so that they're uniformly spread in A at 10 nodes between redshift 0 and 3, and 1 node at the high redshift, basically redshift 1000. And we put a cubic spline to them. And then we use, now that we have continuous forms of these functions, we use mgcam and mgcosmMC to produce all the observables and sample the parameter space. Then we do it with and without a correlation prior that we derived before from Horndeski theory. So now I'll mention this in a minute. This correlation prior essentially suppresses the high frequency features in these functions to make them consistent with the theoretical prediction. And this is following the method which we introduced some 10 years ago with Rob Crittenden and Gombo Zhao in this paper, Fables of Reconstruction. And this is the data that we use. These are the usual suspects. I'm not going to go in great detail. When putting the shoes prior, we will be using this magnitude of the supernovae as opposed to a prior on H0. And our baseline data set that's always considered is CMB plus BAO plus supernovae. And then we add other data sets and consider reconstructions with and without them. Now, just quickly about the priors, the way we obtained them was by using the EFT description of Horndeski, which has 5 functions of time. And then we randomly sample these 5 functions and generate many, tens and hundreds of thousands of Horndeski solutions, and then project them on these functions omega x, mu, and sigma, and eliminate all unphysical solutions, and then find correlations between them. And that's what we're going to use. So this is how the correlation prior looks in the function space. On the bottom here is the prior introduced by the cubic spline. And you can see that it's much less correlated. In other words, once we apply the Horndeski prior, any dependence on actual parameterization disappears. And this is the reconstruction. This is preliminary, but the paper is practically very complete and will be ready soon. So on the left, there is the reconstruction without applying the prior, and on the right is with the Horndeski prior. The top panels show the background dark energy density. You see that without the prior, you see wiggles, which are due to BAO and supernovae data. But as you apply the prior, those wiggles disappear. The most important thing here that you see is that sigma, which is G light, is different. It's higher than what you expect. There are 2 reasons for it. At low redshifts, it's trying to compensate for the deficit of the large scale power in a CMB-TT, because larger sigma creates more ISW, and that reduces the ISW effect in a CMB-TT. At high Z, it's compensating for the famous CMB lensing anomaly, which is that parameter AL. So that if you allow for AL, the value of sigma, if you look at the bottom plots, then you can see that the AL, basically sigma goes back to 1 at high redshifts, which confirms that this was caused by the AL anomaly. We also can project this on the gravitational slip. And I realize, of course, that the significance of this departures from 1 are not super big. But if this was, let's say, at higher significance, then you could say that this ruled out Brans-Dicke theories, because we clearly see that gamma at high redshifts is greater than 1. Now, what about quickly about the tensions? Now, weak lensing, like the tension of S8 comes from, it's the tension between prediction from CMB and actual weak lensing surveys, such as DES and KIDS. And DES and KIDS constrain average sigma times S8. They don't, once you allow for sigma, that's the parameter. So when you allow for sigma to vary, the S8 tension is solved, but it doesn't mean the tension is eliminated. The sigma S8 is still anomalous, so the tension remains. However, if you allow for this AL to vary, in other words, if you eliminate the CMB lensing anomaly, then the tension disappears. So you can solve the S8 tension if you allow AL free, but otherwise you cannot. The H0 tension, of course, is slightly reduced because you allowed for more freedom in the expansion history, but the Horndeski prior makes it more difficult. And this is a plot that illustrates why it's difficult in general to solve the H0 tension with low redshift modifications or recent modifications of gravity. You see the basically luminosity distance predicted by Planck around 0, and differences from it, where Pantheon set of supernovae is plotted here, normalized to shoes. And you can see the BAO data is calibrated on CMB, it's on top, while Pantheon data tries to pull things down when it's normalized on shoes. And the curves here are our best fits. And it's very difficult basically to fit both BAO and supernovae with such things. So that's the reason you don't do better with the H0 tension. And implications for theory, so lambda CDM, of course, is under some tension. Preliminary estimates of significance are close to 3 sigma, but we're still evaluating exactly how to assess that. And as I mentioned, we find gamma greater than 1, which would rule out Horndeski. We find some evidence that sigma and mu are not equal, and that's an indication that it would rule out things like cubic Galileans. But we find no violation of this conjecture that sigma -1, mu -1 have to be greater than 0. And that's the plot showing that quantity. So in conclusion, I believe this is the first time that these 3 things were reconstructed simultaneously. And we have shown that we can learn quite a bit from the data, much more than you would learn from W0 WA. And some of the things you learn is that you can rule out not just lambda CDM if significance becomes big enough, but you can actually rule out some broad classes of Horndeski. And I know I misjudged my time, so I'm going to stop. Okay. You need to unmute, Alexei. Unmute.
Okay. Thank you for a very interesting talk. Any questions? Actually, that may be asked directly or using raising hand. I don't see any
or in the chat. Yeah.
Yeah, maybe by chat. Yeah.
Can I ask one question?
Yeah.
Yes, please, Herman. Come on.
Yeah. Thanks, Levon, for very interesting talk. Just one thing, which is more like a philosophical approach. I mean, don't you think that maybe the best target or first target could be just to rule out lambda plus GR, then, you know, trying to rule out a class of other models as well, you know, to focus the power of the data and the statistics to practically says that, okay, we can rule out, you know, significantly, because as you've shown, the quality of the data is not really that good that we can basically yet rule out any specific model.
Yeah, this is just a reconstruction, and how you interpret it is up to you. I'm just making a point that, for example, lambda CDM is included in Horndeski. So if you rule out Horndeski, you also rule out lambda CDM. It's just that you can do more with this than just lambda CDM.
But I mean that still, for the first step, we have a long way to go, right? I mean, I think it's just a bit too ambitious, you know, to.
I don't think so. I think, so this is current data, and we have some significant detections of gamma not equal to 1, for example. So with future data in the next couple of years or whatever, few years, this will get much, much better. So if you detect gamma not equal to 1, there is a lot of information there. It's not just that lambda CDM is ruled out.
Actually, I think if gamma not equal to 1 appears also in the case of warm dark matter. In particular, it's not so for neutrinos, but the amount of real neutrinos is small.
Yeah, as anisotropic stress. Yeah.
My whole point is that we need to rule out gamma equal to 1 significantly statistically, and I think that is still far away. Particularly, you know, all these models are not really resolving all I mean, they are not really fitting all different data pretty well, right? So I think it just looks to me a bit too early to say that we are going to rule out, lambda or gamma equal to 1 or a class of all Brand-Zeki models. Yeah, anyway, let's see with the future data.
Yeah, you can just look at the reconstruction and make your own deductions. The reconstruction itself is quite agnostic about what you make.
Okay. Thank you.
Okay.
Fantastic once more. But we have to go to the next talk by the Dr. No Ene Frusciante. If I'm sorry if I pronunciate your name, if my pronunciation is not correct.
Hello.
Hello.
Do you see my screen?
Your title, Probing Modified Gravity with Cosmology and Solutions to the Hubble Tension. Please.
Hi, everybody. Can you see my screen?
Yes, yes.
Okay, great. Okay. I will also discuss about going beyond the lambda CDM model. That is mostly due to the fact that the cosmic acceleration now is a matter of fact, and as well as the need for this dark energy content, which is about the 68% of the energy budget of the universe. And if we talk about the cosmological constant as the source of this cosmic acceleration, we face some problems, such as, for example, the cosmological constant problem and any other theoretical issue that we already know. And recently, to these theoretical problems, there are also these additional observational tension, such as the one in the H0 parameter and the sigma 1. So we are talking about tension of around 4 or 3 sigma. Okay, so if we go beyond the lambda CDM model, we can construct theory with a speed of propagation for the tensor mode that is different from the speed of light. So as Levon was telling before, for example, if we consider scalar tensor theory, we can write a very general equation of propagation for the gravitational waves, which has in particular two modification that enters here, which one is in the friction term, and the other one is in the propagation of the speed of propagation, which is given by this parameter alpha t. So according to the detection and the measurement of the associated to the gravitational wave 170117 and its electromagnetic counterpart, we know that the deviation of the speed of propagation of this tensor mode with respect to the speed of light is constrained to be of the order 10 to minus 15. So it's true that these constraints maybe need to be applied at the present time, and we can have open minds to have a late time, an early time deviation in the speed of propagation of gravitational wave. But in this talk, I will focus on having this deviation to be exactly equal to 0. So practically, the theory that I'm going to talk about are practically consistent with the gravitational wave detection. So I will focus on the Horndeski and the Horndeski class of theory, and this is the action that results after we apply the constraint on the gravitational wave alpha t equal to 0. So we have this black part of the action, which is the Horndeski one, and the blue one is the one associated when we extend the Horndeski to beyond Horndeski theory.
Sorry, Noemi, sorry to interrupt. I think we are only seeing your title screen, your title slide. No?
Yes, we can see only your.
Okay. Can you see it better now?
Yeah. I just sent you a chat. Please.
Second slide.
Okay.
Second slide with effective. Okay. And now it is after usually. Okay. And now about Horndeski.
Okay. So but now you can see the full screen, right?
Yes.
Okay, so I can go on from here. So I was just telling that this is the Lagrangian that I'm going to use in this talk. So I will practically fix some functional form for the G2, G3, G and B4 function, and then construct some theory that I'm going to test. And in order to explore the phenomenology of this theory and to provide cosmological constraints, I'm going to use EFT-CAMB, which is a patch for the public Nelson-Boltzmann code CAMB, which implement the effective field theory approach to cosmic acceleration. The code is public available, and it has been developed by me, Bin-Hu, Marco Raveri, and Alessandra Silvestri. So probably the first model of Galilean that has been tested is the covariant Galilean, where the form of the G function is the one that is written here. And the very nice characteristic of this model is that it allows for having a large value of the H0 parameter, which should be, which is in agreement with what are the local measurements. However, the gravitational wave constraints set that G4 and G5 need to be equal to 0. So these two are ruled out. And the only one that remains is the Lagrangian made by G2 and G3. But if we use Planck data, BAO, supernova, and Lensing data, we can do a statistical analysis and compute the Bayesian evidence factor, which tells us that the model is ruled out by data. However, this feature of the H0 is very nice. So according to this characteristic, many other models have been constructed starting from the covariant Galilean model. One of these is the Galilean Gauss condensate model, which extend the covariant Galilean by including the Gauss condensate term, which is proportional to x to the second. Or if you want to go beyond Horndeski, another term that can be added is a beyond Horndeski term here, which includes this other term proportional to x to the second. Hereafter, I'm going to discuss results and constraints in terms of these dimensionless parameter. In particular, when we are dealing with the Galilean Gauss condensate, we are going to have x4 equal to 0. In particular, this alpha h parameter define, every time it is different from 0, define a deviation with respect to Horndeski theory. Let's start with the background evolution. You can see from this plot that the equation of state for the dark energy associated to the Galilean field is different if we consider the cubic covariant Galilean or if we consider the Galilean Gauss condensate. Not only at early time, but also at late time. Here you don't see the beyond Horndeski just because at the background it is exactly the same as the Galilean Gauss condensate. If we go at the perturbational level, we can see that the Galilean Gauss condensate model modify the evolution of the gravitational potential psi here at late time, while the beyond Horndeski has the property of modifying it not only at late time, but also at early time. The reason is because in case we have an x4 parameter, which is quite large at early time, this allows to have this kind of modification. The same behavior can be also seen here if we look at the ISW source, which is the time derivative of the sum of the gravitational potential. We can notice that the model with a large x4 parameter allow for having an early time modification, while in case it is smaller compared to the other x parameter, the modification instead appear only at late time. This characteristic, of course, reflect on the shape of the TT power spectrum and on the Lensing power spectrum. We can notice, for example, that a modification in the real time give a contribution to an early ISW effect, which modify the amplitude of the first acoustic peak in the TT power spectrum, while modification in the ISW at late time modify the tail, and here we see a zoom, and the tail of the low L tail of the TT power spectrum. If we instead go to the Lensing power spectrum, in all cases, we find an enhancement of the Lensing potential, except for the case with the large x4 parameter. We used different combination of dataset. In particular, we have used Planck CMB data alone, and then in combination with the BAO, redshift space distortion, and supernovae data, what we call here PBRS. And these are the constraints in the case of beyond Horndeski model. These are the constraints for the x1, x2 parameter, and here the constraint for x3 and x4. We can notice that the parameter defining the beyond Horndeski function is constrained to be of the order 10 to minus 6. While in this other plot, we can discuss here the result that we have for H0 and sigma 8 compared to the lambda CDM model and the tension with the reset tool 2018 in the top figure. And we can see that instead, in the case of the sigma 8, the tension is not alleviated, as the sigma 8 is practically the same as for the lambda CTM. If we instead consider x4 equal to 0, we reduce to the Galilean-Gauss condensate model. In this case, we use the same combination of dataset, but we also include the CMB lensing data. We can notice that the inclusion of the CMB lensing has a great power in constraining not only the parameter of our model, but also the cosmological parameter. And what we can see here is that these are the values that we obtain for the H0 parameter, and this is in agreement with the local measurement of the H0 at 2 sigma. However, so we know that when we use modified gravity, we have extra parameters. So in this case, for example, for the Galilean-Gauss condensate, we have 3 extra parameters. In the case of beyond Horndeski, we have 4 extra parameters. So it is expected that somehow this model can, in principle, accommodate better the data and offer a better fit. So indeed, if we look for the difference of the chi-square, the effective chi-square between modified gravity and the lambda CDM, we can notice that the modified gravity model offers a better fit. However, in order to account for not only for the goodness of the fit, but also to account for the complexity of the model, we computed also the deviance information criteria, and then we compute the difference between these parameters obtained for the modified gravity model and the one for the lambda CDM, and we found that in the case it is positive, we don't have any evidence in favor of modified gravity. So, for example, in the case of beyond Horndeski, the inclusion, the better fit does not compensate the complexity of the model. Instead, in the case of Galilean-Gauss condensate, we find that this difference is smaller than 0. So, practically, in this case, the modified gravity model is favored by data over lambda CDM. So, the goodness in the fit is also able to account for the more complexity of the model. In order to quantify this preference for the modified gravity model, we computed the Bayesian evidence factor, and we found that every time this is larger than 2, there is a strong evidence in favor of modified gravity model. So this is, for example, the case of the Planck and the combination with the Planck PBRS data. However, when we consider also the lensing, we found that the deviance information criteria is positive, and the Bayesian evidence factor is 1.6, so it is smaller than 2. So in this case, we cannot say exactly if it is preferred or not over data in case of the lensing. The Galilean-Gauss condensate model, since it offers a better fit to the data, has been also investigated at nonlinear scale, in particular for what concerns the Weinstein mechanism, and this will be discussed in the next talk by Francesco Pace later on. Another model that we can consider is the generalized cubic covariant Galilean model, which is also a modification of the original cubic Galilean, but in this case, instead of having just x, we have x to some power. In order to make an analysis, we have defined these other 2 parameters, these S and Q, and we can notice that S is the only parameter that enters in the background evolution. So these 2 models that we show here are obtained having 2 different expansion history. Have 2 different expansion history because they have 2 different values of S. While if we go at the perturbation level, also Q enters in the game, so we can play with 2 parameters instead than 1. In the case of the cubic Galilean, these are the value that S and Q take. So we can notice that the two generalized cubic covariant Galilean model compared with the G3 model, which is the green line, offer a suppressed ISW tail in the TT power spectrum and also a lower enhancement in the Lenzing power spectrum. In particular, this aspect will be important when we compute the statistic and we constrain the model with data, as this is one of the main reasons why also the Galilean Gauss condensate model is preferred by data with respect to lambda CDM. So before we move to the constraint on the S and Q parameter, let me show here that since here we have also included massive neutrino in the game, we notice that if we compare the constraint with respect to those obtained for the lambda CDM model, we notice that we can obtain a lower upper limit, a lower limit for the sum of the massive neutrino of this type, what is not obtained in the case of lambda CDM. And this is a very, very nice result that can be, for example, of interest for experiment like Catherine, which aims at finding absolute mass scale for the neutrino. Let's now move on the discussion about the H0 tension. We can see from this plot that the H0 tension is not present in the Galilean Gauss condensate model, but we can notice that if the tension is not present if we consider only Planck data, but if on top of the Planck data we include the BAO data, we see that another tension arises here. But in this case, it's between local measurement and BAO data. While in the case of Planck, this is perfectly, as you can see here, this is perfectly in agreement with not only with receptor but also with these other measurements. So finally, these are the contour plots for the two parameter S and Q of the model. Here we have also included this area that you see with black lines correspond to value of negative ISW galaxy cross correlation. So all this part of the contour plot is give rise to a negative cross correlation, while this part of the plot still allow for having a positive ISW galaxy cross correlation, which is what data tell us to be. As for before, we have computed the statistics. So we have not only computed the difference in the chi-square, but we have also computed the deviance information criteria, and we find that in all cases the modified gravity model offers a better fit to the data. However, only in the case with the Planck data, the complexity of the model justify the goodness of the fit. So only in this case the model is preferred by data over the lambda CDM1. In this case, we cannot say nothing just because this number don't say precisely the direction if it is preferred lambda CDM or the modified gravity model. So in conclusion, so we have three main messages. The first one is that if we allow for having a parameter characterizing beyond Horndeski theory, these are constrained to be of order 10 to minus 6, but we don't find any evidence in favor of this kind of deviation. If we consider Galilean Gauss condensate model, we find that this model is preferred by data over the lambda CDM, and the H0 value that we found is consistent with its direct measurements up to sigma. In the case of the extended Galilean, so the generalized cubic covariant Galilean, we find again that H0 is consistent with the local measurement, in this case at 1 sigma. And we also find that there is a region of the parameter space for the S and Q parameter characterizing the modified gravity, which allow for a positive ISW galaxy cross correlation. And that is mostly due to the fact that both these two models allow for a better fit to the ISW tail. So thank you for your attention.
Thank you.
Okay, thank you.
We have time for one short question. Please stop sharing screen. Okay. Any short question? Okay. If no question,
Yeah, sorry. May I ask a question on the neutrino masses? Yes, so I find it very surprising the fact that the limit that you have obtained is a lower bound. Cosmology always puts an upper bound so that massless neutrinos are always allowed. So can you comment on this?
So for what we have found, I cannot say, I mean, much, but this is something that seems to be somehow characteristic of the Galilean model, because also when we have tested the cubic covariant Galilean, not only its extension, we have found a lower bound for it.
Okay, thank you. You have to go to the next talk. Let's thank no once more. And the next talk is by Dr. Camille Bonvin, testing the equivalence principle on cosmological scales.
Okay. Okay, so can you see my screen and the pointer?
Yes.
Thanks.
That's okay. Please.
Okay. So today I would like to talk about a test of the equivalence principle, so the weak equivalence principle for dark matter, using the large-scale structure of the universe. So if we look at our universe at late time and at large scale, we can characterize it in the following way. So we have a homogeneous and isotropic background, which is expanding. And then on top of that, we have 4 fields that describe the departure from this background. So we have the 2 metric potentials, psi and phi, that describe perturbation in the geometry. And then we have the density perturbation of dark matter, which I call here delta, and the dark matter peculiar velocity v, which describe the velocity that dark matter halos have in addition to the Hubble flow. Now, of course, in general relativity, we have specific relations between these different fields. And if we modify the theory of gravity, we modify generality's relation. So if we want to test the law of gravity in a very generic sense, what we want to do is to test the relation between these different fields. Now, from an observational point of view, the quantity that we can measure from the large-scale structure are the following. So from gravitational lensing, we measure the sum of the 2 metric potential, phi plus psi, so either with cosmic shear or with CMB lensing. And then by looking at the distribution of galaxy in redshift space, so by looking at redshift space distortion, we measure the density fluctuation of the galaxies and the peculiar velocity of the galaxies. And what we usually do in the linear regime is to relate the density of the galaxy to the density perturbation of the dark matter with the bias. And we assume that the velocity is unbiased, so the velocity of the galaxy is the same as the velocity of the dark matter halos. Now, if you look at this picture, you see that there is something missing if we want to test the relation between the different fields, because we have only 3 measurements and we want to test 4 relations. So what is usually done in standard large-scale structure analysis is to assume something on top of this observation. And usually what is assumed is the validity of Euler equation. So we assume that the way dark matter halos fall into a gravitational potential is not affected by the modified theory of gravity, so that there is no 5th force acting on dark matter. And so from the measurement of the velocity, we can then infer the gravitational potential psi. And then we can do the test that we want. So then from this psi, we can compare it with the lensing to measure the anisotropic stress. And then from the phi that we infer, we can compare with the density to test the validity of Poisson equation. But what you see from this very simple picture is that if Euler equation is not valid, if dark matter does not fall in the gravitational potential in the standard way, then the psi that we infer is wrong. And so the test of the anisotropic stress and the test of Poisson equation are actually incorrect. So what I want to show you in this talk is that we can overcome this problem by looking at the so-called relativistic effect in the large-scale structure. And I will show you that this relativistic effect provides an independent way of measuring directly the gravitational potential psi. So we don't need to assume the validity of Euler equation. We can actually test this relation, and then we can test in a completely consistent way for the anisotropic stress and Poisson equation. So what I will do in this talk is the following. So first, I will show you what is the expression for galaxy clustering, including these relativistic distortions. And then I will show you how we can actually isolate among all the relativistic distortions that we have, the term we are interested in, which is sensitive to the gravitational potential psi. And then I will show you how we can use that to test the equivalence principle for dark matter. So in practice, once we receive a map of galaxy, like this one from SDSS, what we do is to split it in bins of redshift and solid angle. So we pixelize the map, and then we count how many galaxy n we detect in each of these pixels. And the quantity we are interested in is the fluctuation in the number of galaxy from pixel to pixel, which I call here delta. So it's simply the number of galaxy in a pixel minus the mean number and divided by the mean number. So the standard way of modeling theoretically this observable delta is the following, which has been done by Kaiser and Hamilton in the 80s. So this theoretical modeling tells us first that the distribution of galaxy follows the distribution of the dark matter up to the presence of the bias. And then we have this correction here, which is the well-known redshift space distortion corrections, which tells us that if we have a gradient of velocity in a pixel, this will actually change the observed side of the pixel in redshift space, because Doppler modifies the observed redshift. But if you think a bit about this expression, you understand immediately that we expect other distortions beyond this redshift space distortion. First, because the redshift itself is not only affected by Doppler effects, but it is also affected by the presence of gravitational potential wells. And then also because the direction of propagation of the photon is affected by the large-scale structure between the pixel and the observer. So it is length, meaning that the solid angle in which we count how many galaxies we have is affected by lensing. And finally, the luminosity of galaxy is also affected by lensing, which will change the number of galaxies that we see above a given threshold. So it's possible to do a derivation of this observable data, taking into account all these effects in a systematic way. And this is what we obtain at linear order in perturbation theory. So in addition to this standard Kaiser expression, we have here the effect from gravitational lensing in the second line. And then in the last three lines, we have the effect is relativistic distortion term. So these effects are actually subdominant with respect to the standard terms and negligible for current survey, but we expect them to become important for the coming generation of survey. And if you look at this relativistic effect, you see that there is among them the term we are after, which is this effect here, which is proportional to the gradient of the gravitational potential psi. So if we can measure this term and compare that with the contribution from redshift distortion, we can then test for the validity of Euler equation. Now, of course, what we need to do this test is to isolate the contribution from gravitational redshift, because, of course, what we measure when we measure delta is always the sum of all these contributions. But we have a way of isolating this term, which is by looking at the correlation function. So once we have measured delta in different pixels in the sky, what we usually do in order to compress the information is to look at the correlation of delta at different positions in the sky. So we correlate delta over two different pixels separated by the separation d, and then we average over all possible pairs that we have in the survey. Now, in order, the standard redshift space distortion analysis, what they do in order to extract the information from this correlation function is to weight the two-point correlation function by the Legendre polynomial here, where the argument of the Legendre polynomial, this beta, is simply the cosine of the angle that the pair of pixels makes with the direction of observation. So if we look at the part where L is equal to 0, this means we simply average over all pairs without any weighting. What we do is to isolate the monopole part, which depends on the density fluctuation. Whereas if we look at the L equal 2 and L equal 4, the quadrupole and hexadecapole, we target the contribution from the peculiar velocity. So in this way, we can measure separately density and peculiar velocity. And this is what has been done in many surveys in the past. Now, the effect that we are interested in, this gravitational potential term, has the specificity to generate other multiples in the correlation function. And in particular, what they do is to generate a dipole in the correlation function. So if we fit for a dipole in the data, we will actually isolate this contribution from gravitational redshift. Now, if you think a bit about it, you see immediately that if we have just one population of galaxy, we cannot measure a dipole in the correlation function, because by construction, the correlation function is invariant if we go from beta to beta plus pi. So if we exchange the position of the pixel in the pair. However, if we take our population of galaxy and we split that into two populations, a bright population and a faint population, then we can look at the cross correlation between the bright and the faint, and we can measure a dipole in this cross correlation, which will be non-zero. So let me just spend a couple of minutes trying to explain to you intuitively why we expect such a dipole in the correlation function. So let me consider this very simplistic situation where I have an observer here who looks in this direction, and the observer sees three galaxies, one behind the other, all aligned in one direction. In the middle, there is a bright galaxy, and then there are two faint galaxies, one in front and one behind the bright one. Now, let me assume that the bright galaxy sits at the bottom of a gravitational potential. This is actually what will happen in average in large-scale structure survey, because the brightest objects tend to be at the bottom of gravitational potentials. So if we look at the light emitted by this galaxy, it has to climb from the bottom of the potential up to the observer. So the photons lose energy, meaning that this galaxy is shifted to the red by the presence of the gravitational potential. So in redshift space, it appears a bit further away from the observer than it is in real space. Then if I look at the faint galaxy in front, so this galaxy is also inside the same gravitational potential, but not exactly at the bottom, a bit higher up in the outskirts. So the light also has to climb out of the potential. So this galaxy is also shifted to the red, but by a smaller amount than the bright galaxy. And then if we look at the faint galaxy behind, I have chosen here a symmetrical situation. So the redshift experienced by the faint behind is the same as the one experienced by the faint in front. So now if I look at the separation between the galaxies in redshift space, what I see is that the separation between the faint behind and the bright, DE1, is now smaller than the separation between the bright and the faint in front. And because the correlation depends on the separation between the galaxies, it means that the galaxy behind is not correlated in the same way as the galaxy in front. Okay, thanks. So of course, this situation is very simplistic, but actually the idea is the correct one. So if we do the calculation properly, without assuming any of the simple thing that I said there, what we find is that due to this gravitational potential, there is a dipolar modulation in the amplitude of the faint galaxy around the bright one. And so we can target this effect by simply fitting for a dipole in the data. Now, if I go back to the expression for delta, I can actually easily show that this gravitational redshift term, grad psi, is not the only one that generates a dipole. There is also a contribution from these two velocity contribution. But this is not a problem because we already have a measurement of the peculiar velocity from redshift space distortion. So the idea to test the validity of the equivalence principle is actually to combine the different multiples in such a way that the combination vanishes if and only if Euler equation is valid. So Euler equation has the following form. It relates the time derivative of the peculiar velocity to the gradient of psi. So of course, we cannot directly reconstruct this equation because we look at correlation. So what we are after is the correlation of Euler equation with delta. And so the idea is actually to combine quadrupole, hexadecapole, and dipole in order to reproduce this term here in the left-hand side. So if we look at the dipole, the correlation in a dipole contains two of the terms that we are after in Euler equation, delta V dot and delta grad psi. And so the game to play is simply to add the correct amount of quadrupole to the dipole in order to reconstruct the delta V term here, and then to add the correct amount of hexadecapole in order to cancel the VV term. So we built this null test here, which is a combination of dipole, quadrupole of the bright and faint, and hexadecapole, such that this combination is equal to 0 if Euler equation is valid, and it's different from 0 if Euler equation is not valid. So just to give you an idea, for example, if we have a scalar tensor model or a vector tensor theory of gravity, where the scalar or the vector field mediates gravity, and if this field is non-minimally coupled to dark matter, then we violate Euler equation in the following way. So we add a fifth force which acts on the velocity of the dark matter halo, and we also add a friction term. So at the moment, we can unfortunately not apply this test to data simply because the dipole is too small to be detected in current survey, like for example in BOSS. But we did some forecast for the coming generation of survey, and we found that for DAISY, that has actually already started to take data, we expect a signal to noise ratio for the dipole of 10, and for SKA2, which is more futuristic, a signal to noise of 46. So we expect in the near future to detect this dipole robustly, and then we will be able to apply this test. So given that we will be able to apply this test, we can ask ourselves the question, which type of deviation from the equivalence principle can we detect? So the sensitivity of the null test depends, of course, on the variance of the null test, for which we have a cosmic variance contribution and a short noise contribution. So we did the forecast first for an ideal survey. So assuming that we observe 30,000 square degrees of the sky with no short noise, so we are cosmic variance limited. And then we found that we will be able to detect at 3 sigma a violation of the equivalence principle of the order of 10 to the minus 2. And then if we add the contribution from short noise, so we use the specific of SKA, we degrade quite a lot the sensitivity of the null test, but we can still detect a violation of the equivalence principle of the order of 0.8 at 3 sigma. So this is very exciting because it would really be the first test, direct test of the equivalence principle for dark matter that we can have. So to conclude, relativistic effects in large-scale structure are actually very interesting. They will be detectable in the coming future, and they will provide new information, so something that we cannot measure with standard way, which is this gravitational potential psi. And so we can use that then to do model-independent tests of some specific property of gravity. Thank you, I'll stop here.
Thank you. Thank you, Camille. Any questions?
I have a question.
Yes, please.
Okay. Thanks, Camille, for a really interesting talk. Yeah, this is very nice. I really like it. So this E break of 0.83, do you have a sense of that number? How does it compare to what you might get from some modified gravity or some alternative theories? Is it a big number or a small number?
It depends. I mean, it is a big number if you compare to deviation in mu, for example, because deviation in mu with future survey, you can constrain them at the percent level. So here it's 0.8, which is 10 to 100 times larger. So in this sense, it is a big deviation. But on the other hand, there is currently no way of testing this breaking of the equivalence principle, because this is something that you cannot access with the standard gravitational lensing and redshift space distortion. So even if it is larger than the modification in the other the other quantity, it is still interesting because it would give us a way to directly test that.
Yeah, thank you.
Okay, any more questions? Okay, can Ine, please stop sharing screen? Okay, yeah. So then let's thank her once more, and we are going to cover the next talk by Dr. Francesco Pace. Let me see. Yes, please share screen.
I hope you can see my screen.
Indeed. Non-linear perturbations in the Galilean ghost condensate model, please.
Yes. Okay. So today I'm going to talk to a recent work of about 1 year, which I was doing with Noemi Frusciante, and this will represent the prosecution of her talk about the Galilean ghost condensate model, and in particular the analysis that we did on small scales in the nonlinear regimes. So the outline of this talk will be just about a short introduction and motivation, which I can basically skip because it's already what Noemi and Levon said before about modified gravity, and therefore I will then directly concentrate on the model. The background has already been introduced by Noemi, so I will just report the Lagrangian and say why we work on that. Then I will briefly present the linear perturbations, and then I will devote most of my time on the nonlinear perturbations, in particular the spherical collapse models and what we found from a point of view of the observables. Okay, so as was said before, the lambda CDM model is accurate, but there are many problems. Therefore, we tend to study dark energy modified gravity models, and one of these modified gravity models, the Galilean condensate, seems to be statistically preferred by data over the lambda CDM model. So this is just described by this Lagrangian, where this term here represents the Ricci scalar. This is the KSS part, let's call it that way. So in terms of your Horndeski function is the G2 function, and this 3A3X box phi represents the G3 function. Now this is statistically further over lambda CDM exactly due to this term here, A2X squared, because the dark energy equation of state goes into the phantom regime during the matter dominated area. So we could study this from an effective field theory point of view, in particular with alpha functions, which were introduced in 2014 by Bellini and Savicki, and they represent a very compact way of discussing the linear perturbations. And since we are just discussing G2 and G3, we only need 2 alpha functions, the alpha k, which is this one and represents the kinetic term, and alpha b, which is this one here, and as you see, depends on A3, it represents the coupling between with the gravity part. In particular, this is the box phi part. Now, as we also saw from Levon's talk, we could discuss modified gravity models using a generalized Poisson and Lansing equation, where in this case, when we usually discuss this generalized Poisson equation, we usually consider a mu which is linear, because this is the one that we can infer from analytical calculations in modified gravity. At the same time, we can also define a sigma L, so this would be G matter, and this would also be G light, which represents the gravitational lensing effect. Now, since this model doesn't have an isotropic stress, we have that both at linear and also later at the nonlinear level, the 2 function mu and sigma will be equal to 1. And they can be written in a very compact form in this way, so they are equal to 1 plus 2 alpha b squared over alpha c squared, where the 1 part, so the constant 1 represents the GR contribution, and this term here represents the modifications of gravity, and the c squared represents the sound speed of the model. And you see, this is a very compact way of writing, because otherwise I would need to use every time this kind of expressions here, which make it very lengthy and difficult to understand what's going on. So the linear perturbations were already studied and shown before. So in this talk, I'm just going to concentrate on the small scales. And when we talk about small scales, since we see that the effective gravitational constant mu becomes different from 1, and there are contributions from modified gravity, then we want to reconcile it with observation, which show that at small scales and in the solar system, the gravitational constant is equal to G Newton and therefore to 1 in this formalism. And therefore, we need to introduce some particular screening mechanism, which for the Galilean model is represented by the Weinstein mechanism, which suppresses modifications in on the solar system scales, and in particular on a high density environment, which means that if we are in a low density region, we could see the modifications of gravity, while if we are in a high density environment, this is not the case and it reduces to general relativity values. So what we have to do, we have basically to determine that, replace that mu L with a mu nonlinear, and this will represent all our nonlinear physics. So what we do is that we start from a generalized Poisson equation, which is written here, and we combine that with a nonlinear equation for the scalar field. So you see that the first part here, so the box phi and the delta phi, psi and delta phi, they represent the linear part which we usually consider, to which we needed to include this additional term here, which represents the nonlinear part of the scalar field equation of motions. Now, since I said before that there is no anisotropic stress, phi and psi are the same, so we can combine the two equations to get a single equation for the, which is this one here, for the perturbed scalar field, and we see that it's sourced by the matter perturbations delta m. Now we need to solve these equations here, and what we usually do is first assuming spherical symmetry, and then considering a top-hat profile. Assuming a top-hat profiles means that we have zero perturbations outside the perturbations and a constant profile inside the perturbations. This is what usually done in cosmology, and in particular also when people study the spherical collapse model, because this helps to simplify perturbations a lot, in the sense that instead of having partial differential equations, we can go back to standard ordinary differential equation. So when we do that, also assuming spherical symmetry and considering top-hat profile, the equation of motion for the scalar field reduces to this one here, and then we can just solve it at the boundary of the perturbation, so on the surface of the perturbations, and what we get is this function here, this expression here, which, as you see, depends on the function R over RV, where R is the size of the perturbations and RV is the Weinstein radius. And the Weinstein radius is proportional to the matter delta M inside the perturbations. And now you see that we can define two different regimes, in particular one when we are below inside the Weinstein radius, and therefore this contribution goes to 1, or when we are outside and then we don't recover general relativity. So now, taking into account the equations of motion of the scalar field, we can go back to our previous definition of the Poisson equations, and we know that the Poisson equation is sourced by all forms of matter of energy being perturbed and acting gravitationally, which means that we can write the Poisson equation as given by two contributions. One is from matter and one is from a perturbed scalar field. But we just saw before that the perturbed scalar field is sourced by matter perturbations. Therefore, we can combine the two previous equations, the one from a generalized Poisson equation and the one from the scalar field. And what we obtain is this modified Poisson equations, where the contribution from the scalar field go into this function, which I call the mu nonlinear. And this mu nonlinear can be written in this simple way, which, as you see, is very similar to what I was showing before for the equation of motion of the scalar field. And also here, of course, we will have two regimes. One when we are, for R going to 0, therefore we are inside the Weinstein radius. In this case, we are in a high density regime, and therefore modifications of gravity will be erased. And as you see, if you can do simple calculations, mu nonlinear goes to 1. If instead we are outside the Weinstein radius, then of course we recover the linear regimes and mu nonlinear becomes again mu linear. So now we could study, having this at hand, we could study the spherical collapse model. So this model describes the evolution of an isolated spherical perturbations. And the physics behind this model is extremely simple, despite all the approximations, and it has been shown actually to work pretty well. And the analytical predictions are usually in very good agreement with the n-body simulations. So what happens in this model is that we consider a small patch of a universe which is overdense and is isolated from the other, and it expands at the beginning with the Hubble flow. But since it's overdense, it detaches from the Hubble flow, slows down its expansion, reaches a maximum, which is usually called turnaround, and then collapses again to a 0. So therefore, the physical size goes to 0. In reality, this is only mathematically, because in reality, virialization must take place because we observe structures. And therefore, if we introduce the virialization theorem and we assume that virialization takes place, then the perturbation reaches a finite size. And when you solve these equations, which is the one here, where now you replace this Laplacian of psi with these equations here. So where instead of having the mu linear, you have a mu non-linear. So instead of having one in general relativity, we have these more complicated functions. We solve this, and the goal is that the way of solving this equation is that we need to find the initial conditions such that at the time of collapse, so the one that we want to study, this delta m diverges. When we find these initial conditions, we can linearize this equation, which basically simply becomes delta double dot m delta double dot plus 2h delta dot equal to Laplacian of psi over a square, and the mu non-linear becomes mu linear, and this is simply the growth factor equations. When we solve this one, we find the linear extrapolated over density perturbation, which is normally called delta c, and is the main ingredient, as we will solve shortly, of a mass function, in particular when we consider the analytical formulation a la Shetland-Thorman, for example. So everything that we need to know is dictated by this evolution of mu non-linear, which is now shown here, and compared to the linear evolution. And here we consider two models. One is the GGC, which is the ghost Galilean condensate, and the other is just a cubic Galilean. And as you can see, in the linear case, which are the blue curves, which are the red and the blue solid curves, then the mu function grows and becomes bigger than 1. When instead we take into account the Weinstein mechanism, we reach a maximum value and then we drop again to 1. In particular, here we go to 1 because we want that at present time modifications of gravity are hidden inside the small scales. So now we can apply the study to these equations to the study of some observable. In particular, I will show the results for a matter power spectrum, which is a powerful tool which can be used to study modifications of gravity. Now, it's easy to derive for whatever kind of modified gravity model at the linear level, but this is not the case when we have to study nonlinear scales. So when we do this, we need to take into account screening mechanism on nonlinear scales, nonlinear corrections, and most of the times what we can only do is run n-body simulations and eventually do some fit about the result and then study what happens. Here instead we consider a different approach, which is more phenomenological, and in particular we study this time evolution and scale dependency of a nonlinear spectrum. So you can see that there is a function here at the beginning, which is the ratio between the nonlinear matter power spectrum in the lambda CDM over the linear one, and this is the transfer, an effective nonlinear transfer function which maps the linear spectrum to the nonlinear spectrum. And here on the right side, there is a correction which is suppressed by a functional form which goes like k over ks, where ks is the screening scales. In particular, for scales bigger than the screening scale, this terms becomes 0, and we recover the lambda CDM model. Now, what you can see is that this model, in fact, this formulation gives a lot of differences at large scales, because the two models, when using their best fit parameters, look different. And in particular, this gets amplified because the power spectrum practically goes like sigma square. And you see that differences on large scales are of the order of 20% almost. While when we go to small scales, they become much smaller, may become, of course, of the order of only a few percent because the screening mechanism takes place. Of course, we don't need only to concentrate on the matter power spectrum, but we could also just integrate it along the line of sight, and this would be eventually even simpler with very big surveys, and this would be to the study of lensing power spectrum. So the lensing power spectrum is very dependent on the matter power spectrum, and it's integral along the line of sight. Now, since here we have to take into account that the lensing is not GR, we have to introduce this function as shown before, sigma square. And of course, since we also don't know how this gets screened in a simple way, except plugging the mu again as before, we used a widely used approach where the sigma gets screened on scales smaller than the screen scales. So as before, on large scales, we also saw that there were many differences between the Gauss Galilean and the lambda CDM model. Also in this case, we are going to see that, as you can see here, there are differences of about 20% between the Galilean model and the lambda CDM model. So you see that where differences are quite enhanced, and it will be quite simple to determine that observationally. And in particular, you also see that increasing the screening scales, the differences, the agreement between the modified gravity model and the lambda CDM model gets pushed to very small scales. The last observable that we found, what we analyzed, is the study of the mass function, which represents how many halos in a given mass and a given time we are going to observe. Now you can see also 3 different redshift, 0, 0.5, and 1. And as expected, that the farther we go in time, the higher are the differences between the 2 models. And this is because the differences grows exponentially in the high mass tail, and of course, because there are differences in the growth factor and in the evolution of the delta C function, they get enhanced due to this functional form here. So you can see that also if we will have a quite complete catalog, we will be able, of clusters, we will be able also to use the mass function as an indicator to probe modified gravity with respect to the lambda CDM model. And now just to conclude, we saw that the Weinstein mechanism changes the matter coupling mu, and this is the important function that we have to use to study this kind of models at the nonlinear level. The matter power spectrum is rather different between the 2 models, and same for matter power balancing spectrum, and therefore we hope that this will be observationally better constrained also on smaller scales. What we did was pretty phenomenological, therefore better theoretical approaches for the nonlinear matter power spectrum are required, and then they of course need to be validated with n-body simulations. And thank you for your attention.
Thank you, Francesca. Thank you. Any questions? Francesca, please stop sharing screen. Okay. If there are no questions, let me pass my chairman's duties to David. David, please continue as the chairman. David, unmute yourself.
Sure. Yeah, thank you, Alexei. So next speaker will be Thiago Barreiro. Please share your screen, please.
Okay, thank you.
And the subject will be testing FQ gravity with redshift space distortions. So please go ahead.
Okay, thanks. Okay. Okay, can you see my screen okay? Okay, can you see my screen? Is that okay? Yeah?
Yes, we can see your screen.
Okay, thanks. So I want to talk about this work that was done in collaboration with Bruno Barros, Tommy Koivisto, and Nelson Nunes, where we look at a specific f of q gravity model and then do it some simple tests looking at redshift space distortion data. But just to start, I mean, we've all been here today, right? So I think we're praying to the converted that the question is basically, do you need to go beyond lambda CDM to explain dark energy? And I think we can all agree that, I mean, lambda CDM as a dark energy model has been holding up pretty well observationally for the last 20 years or so. We have some cracks that start to appear, right? I mean, as mentioned today several times, this H-naught tension between local measurements and CMD, and also for large-scale structure, sigma-8 measurements that contrast with the CMB value. So there could be some hints here that lambda CDM is not really appropriate as a right description of dark energy. But I think we can all agree that the jury is still out to really know. So the question is, I mean, what sort of models beyond lambda CDM can we have, and are they needed to explain the data? So I'm not really going to go into H-naught tension today, as you will see, because I'm going to focus on the lambda CDM background. But we'll use the large-scale structure data, right, to look at how we can sort of alleviate this sigma tension between a local measurement of dark energy and the CMB values. So to start from, I mean, from the theoretical side of what inspires our model is different ways of describing gravity, right? So usually to describe gravity, you describe space-time with a metric and a connection. And with these, you can define a curvature tensor, a torsion tensor, and the non-metricity tensor, which is basically the derivative of the metric. And the usual choice in general relativity is to set the torsion to 0 and this non-metricity to 0 as well, right? The covariant derivative of the metric is 0. And you get the Levi-Civita connection, and you describe your space-time physics with the curvature. But actually, the funny thing is that you can do different choices for the connection, right? And actually, you have sort of this several options, right? So at the top, you have this general relativity. Like I said, you set the torsion and the non-metricity to 0, but you can also opt to set the curvature to 0 and use the torsion to describe your space-time, or you can set the torsion to 0 and use your non-metricity to describe space-time. And actually, you can also choose other connections and do things in between, like having non-zero torsion and curvature, for example, and things like that. Okay, so you have several options of descriptions of gravity. The funny thing is that you can define a scalar from curvature, the Ricci scalar R, and you can define a scalar from torsion T, or a scalar from this non-metricity tensor Q. And if you use one of these scalars as your action and pick the right connection, you actually get an equivalent description of the same physical spacetime. That means that your usual general relativity spacetime described by your Ricci scalar R, with the R as your action, can actually be described using torsion with T as your action, or with the non-metricity Q as using Q as your action, right? So these are all equivalent. So this is usually called the equivalent teleparallel description of general relativity, or in the case of the non-metricity, the equivalent symmetric teleparallel description of general relativity. And all these will describe the same physical space-time. They are completely equivalent. Now, if you go to a modified gravity, right? So now if you go to models like f of r, then this f of r, or if you opt to go to an f of t or an f of q, then they will give you different modified gravities. I mean, for a start, because you usually pick a simple function f, right? So obviously having a function of your Ricci scalar won't be the same as having a function of your q scalar or your torsion t scalar, right? So these all will give you different modified gravity models, right? So we're going to focus on picking an f of q type of model. So you basically take an action where you pick an f of q. Again, if your f of q is q, you just get general relativity. Just for to fix your idea, q is obtained from the non-metricity tensor. I mean, we're not going really to use this, but anyway. So this is our start, right? This f of q action. And now if you go to homogeneous isotropic flat spacetime with the Phenomenal-Redson-Walker metric. I mean, to make the metric is the same as for the usual GR, right? Because what we are changing is the connection, not the metric, right? So this is again like for GR, the usual curvature descriptive GR, if you like, the flat Redson-Walker metric. In this case, your Q scalar is given by 6h squared. H is the Hubble parameter, and these are your Friedmann equations here, right? Which are modified by this F here and this FQ. FQ is just a derivative of F with respect to Q, and FQQ is the second derivative. Again, if you plug Q for F, right, you can check directly that this will reduce. I mean, using this Q here, right, for the Redson-Walker one. This reduces immediately to the usual Friedmann equations, both of them. And you can even add a constant to F, right? And because these are the derivatives, it only appears here. So this constant here will just be a cosmological constant, right? Because you can opt to, you know, as usual, you can put the cosmological constant as an extra energy on the right-hand side, but you can also do sort of a geometric cosmological constant, right? And so if you put the constant here, you get the cosmological constant. Actually, C will be 2 lambda if you want, okay? Doesn't really change anything. It's just an option you have. So the funny thing, and it might not be apparent looking at this directly, but if you do the calculations, you realize that you can also add a square root of Q term, right? This was done by Jimenez et al. In in the papers I cited before, and you get this m parameter, right? You have this mass parameter here, and if you plug this f into the Friedmann equations, you realize that you recover the usual Friedmann equations, both of them, right? So this is exactly the same as lambda CDM in the background. So the Q will give you the usual MCDM, this square root of Q, and this M parameter basically disappears in your background equations. So it's not there anymore, and it's completely equivalent in the background to lambda CDM. Now, the interesting thing is that if you go beyond the background and look at the perturbations, then this parameter won't cancel anymore, and it will appear, right? So what we get here is a model where the background will be exactly the same as your lambda CDM, but perturbatively, it will behave differently. Namely, if you look at the matter density perturbations, this is the usual equation, right? And as common in modified gravity kind of models, you have a modification here in the term with G, right? So it's basically the same as considering the effective gravitational constant that is given by G divided by the derivative of your F function. And for the F function we picked, which had that Q and the square root of Q with the M parameter, and using Q as 6h squared, which is one for the flat Robertson Walker metric, then what you get is this effective Newton constant. Now, if your M is 0, again, you recover lambda CDM. So even in the even in the perturbative sector, if you remove the square root, right? If you set the parameter M to 0, you recover exactly lambda CDM. But if your M is different from 0, then obviously you'll get a different evolution. So this is the sort of effect you might expect, right, for the evolution of the derivative of the matter density perturbations. So if you have a negative M, you will enhance the perturbations, and for positive M's, you'll decrease suppress the perturbations, right? And because obviously you can see here that for a negative M, you'll increase the effective gravitational constant, and for positive M's, you'll decrease the gravitational constant. So this is the sort of effect you have at the perturbative level by using this f of q, which mimics lambda CDM exactly in the background. So this is what we want to test. What you are going to do exactly is we'll use three choices, right? First, just setting m equals to 0. This is a pure lambda CDM model, right? So this is both at the background and perturbative level is exactly the usual lambda CDM model. Then we'll just keep m as a free parameter. So we'll try to see what the best fit will be to our model. And third, just as an extra option, we decided to include the cosmological constant in our f, which basically has the effect of using your cosmological constant to fix the value of this m parameter, right? So you link the two, right, in this way. And since this m squared over 4 has to be your cosmological constant, because you're setting lambda to 0 in the other equations if you want, then this imposes the m parameter to be 4, right? So this is a way of extending lambda CDM with no extra parameters, right? Because your extra parameter m is basically fixed as well by lambda, okay? So these are the three models we're going to test. I mean, the first one is just the usual one, right? So we just want to compare with our results. So for that, we're looking at redshift space distortion data. Now, typically, redshift space distortion data will yield you this f sigma 8 value, because this is what you can get. This is sort of unbiased. You don't really need to know the bias to get this. Where f is the growth parameter, right? So just the prime of delta. And for our models, so this is related to the plot we had before, right? You can see that this f sigma 8 is affected in this way. This is slightly different from the other one because this is this has this delta 0, right, scale added, right? And this will be different for different models. So basically the curves cross, right? Whereas before they didn't, because we had the same, we're just looking at delta prime, okay? But again, at small z's, right, we'll increase the power for negative m's and decrease for positive m's. These are shown just for a fixed sigma 8, right, of 0.8, which is around the Planck fault. The Planck is 0.81. So what do we do? To test this, we're going to use 22 data points from several F-sigma observations. So these come from large-scale structure surveys like SDSS and BOSS, etc. These 22 data points were chosen to be self-consistent. So we just take the observed F-sigma 8 and then compare with our theoretical value. We also have this extra R coefficient, which is just an empirical correction for the cosmological parameters, because these experiments are done with some fiducial cosmology in mind. And even though in our case, the connection is quite simple because our background is lambda CDM, the parameters we use, so for our lambda CDM background, we are just using the Planck parameters, to keep things simple. But different experiments will have different fiducial values for these parameters. So just to correct for that, we have this extra empirical term, and this will give us our likelihood that we're going to use to constrain our parameters. Also, so the parameters we're going to constrain is just this M parameter and sigma 8, which we are keeping as a free parameter. We also compute the ICRANet information criterion just to test which models would be preferred, right? This is a way of comparing the chi-square values, the preferred chi-square values, but giving some penalty to extra parameters. Now, in our case, it's a second model with the free M parameter that is penalized, right, by this, whereas both lambda CDM and the third model, where we link M to the lambda CDM to the lambda value, will have no extra parameters, right? Just sigma 8. So this is what we get. So these are the data points you use, right? So this is the F sigma 8 values coming from the observations. And here, the black line is just the usual lambda CDM value. So it's this result that will give you, as we'll see soon, the sigma 8 value, which is lower than the Planck usual CMB value. And then the best fit you have for the free model with the M is just this dashed line here. And the dotted line is the one where we fix the M parameters in lambda. So both the top line and the bottom line are just constraining sigma 8 because M is fixed, whereas the middle line, we're keeping M free, right? So the values we have here is these M's are given in the units of H0, by the way. So lambda CDM obviously has no M parameter. It's 0, right? It's just the usual. And the sigma 8 is 0.75, which is different, lower than the Planck value. That's okay, thank you. Yeah, 15 minutes. So it's lower than the Planck value. And so if you keep our M free parameter, we'll get the best fit of around 2 and the sigma 8 of around 0.83, which is closer to the Planck value, as you can see. And if you fix M with lambda CDM, funnily enough, which our M is 4, then it's really much higher than the best fit value if you keep it free, obviously. And consequently, we also get a much larger sigma 8, right, around 0.9. Now, if you look at the information criterion, you can actually statistically infer that the last model is preferred, though they are all quite close, so there's no real statistical significance here, okay? Obviously, this one, because it has an extra parameter, is not really that much favored compared to the other ones. But if you look at the actual data, right, this is what we get. So this is the lambda CDM result here with a smaller value of sigma 8 and 0M. And this is the one where we fix M with the lambda value. And this is just the best fit, keeping M as a free parameter. So if we look at how our sigma 8 behaves, right? So for the free parameter M here, which is the right plot, you can see that your sigma 8, so this red value here is just the Planck sigma 8 result, right? So here you can see that they are quite close. So if you keep M free, of course, we have this extra parameter, so it's expected that it's easier to fit the data. Whereas the usual result with lambda CDM is a lower sigma 8 compared with Planck. And as I said before, if we fix M with the cosmological constant, then we get a higher value than the Planck result. So in summary, we looked at two specific F of Q models to test with a lambda CDM background. Those models with the model 2 parameters have, sort of alleviated the tension, sigma 8 tension with Planck, which is to be expected because we also had an extra parameter. And the other one with just one parameter is actually statistically favored, but has, as you saw, quite a large tension with Planck. So anyway, this is something that will be much more fine-tuned in the future because the observations will improve enormously in the next few years, right? So this is the type of models that will be really exciting to test in the future. Thank you for listening. That's it for me.
Okay, thank you very much for this interesting talk. Please unshare your screen. Okay, are there any questions? Okay, if not, let's thank our speaker again. And next speaker will be Elsa Texera.
Well, can you see my slides?
Yes, yes, we can see it. So the title is Observation Constraints on Dark D-Brain Cosmology. Please go ahead.
Thank you. My name is Elsa Teixeira. I'm a PhD student at the University of Sheffield. And again, my title is Observational Constraints of Dark D-Brain Cosmology. So as we have heard in the previous talks, we have now overwhelming observational evidence for the accelerated expansion of the universe from different data sets. This can be explained in the context of the lambda CDM model that follows a rough distribution like the one we see here. We know that this model is successful in predicting the cosmic background radiation measurement and also the large-scale distribution of galaxy. But as we have already seen again in previous talks, we know that this model suffers from conceptual problems and also some tensions between observations. So as an example of one of these tensions, we have the famous Hubble tension. So this is really just the fact that we have unreconcilable values for the present Hubble rate, so for the parameter H0, coming from the CMB measurements and also from direct local distance ladder measurements. One of the most extreme cases that we see here illustrated in the figure is the discrepancy between the value measured by the Planck 2018 collaboration and also by the Schuss collaboration. So these values are roughly in 4.4 sigma tension, and we see here the value. So for Planck, we have a rather lower value of 67.4, whereas for the Schuss collaboration, we have a much higher value of 74. It has recently also been suggested that in reality, this should be seen not as a tension in the H0 parameter, but also on the supernova peak absolute magnitude as measured, for instance, by the Pantheon dataset. We also know that these Planck 2018 results are one of the big confirmations of the lambda CDM model, but we also know that they are model dependent, and so in principle, they could also be explained with other models. And so this is also a hint that we'll probably need to introduce some sort of new physics in our models or some extensions to the lambda CDM model. And here I will address one of these extensions, which is couplings between dark matter and dark energy. So,
sorry, somebody has his microphone on. Please switch it off. Thank you. Please go ahead, Elsa.
Thank you. So in order to do this, we want to introduce a non-minimal coupling between the scalar field and matter. In our case, we'll do this just for dark matter. And so one way to do this is to work in the Einstein frame formulation, in which we assume that we have the usual gravitational sector described by the Einstein-Hilbert action, given by the gravitational metric G mu. Then we have the action for the scalar degree of freedom in our theory, also described by the gravitational metric. And then what we do is to assume that the matter fields in our theory are defined according to a physical geometry that is related in some way to the gravitational geometry. And if this metric is also dependent on the scalar degree of freedom, there will be an intimate relation between these two. So the simplest way to relate it to the two metrics, so the gravitational metric and the physical metric, is to take what is called a conformal transformation, which is just a simple rescaling of the metric. If we have a scalar degree of freedom that is already present in the theory, this can be used to parameterize the transformation. And then we can also generalize this to this formal transformation, which is the most general transformation that can be constructed again from one scalar degree of freedom and from the metric, and still leads to second order equations of motion. So this is what we have here, and we see also that we have now two free functions, C and D, and if we set this function D to 0, we recover the conformal transformation. Okay, so this has been studied in the context of a canonical scalar field, so a quintessent scalar field. What we see is that if we have a conformal coupling, we'll have a coupling that is constant throughout the whole history of the universe. And so in principle, this coupling can't be very high, otherwise it would be hard to reconcile it with observations. On the other hand, if we introduce this formal contribution, we see that we are able to suppress the coupling throughout part of the history of the universe and have only a contribution at late times, or at least for just a significant part of the history of the universe. So this means that we have late time modifications when compared with the conformal coupled model. However, we see that if we take just the most simple toy models, so such as an exponential form for the free functions, we have very drastic departures when it comes to formation of large scale structures. And so it's very difficult to reconcile this model with the current observations. Also, since we have a lot of free parameters, if we take an MCMC analysis, we still see that the lambda CDM model is preferred by the data, even if we are able to reconcile it with observations. Also, we assume interactions with dark matter only. Usually, this is to avoid constraints we have on couplings to standard model particles. And we also have, in principle, two free functions, C and D, that can have two or more parameters. And this means that while we are able to describe many generalized theories of gravity in this context, we also have a lot of functional freedom. So there are three things we would like to explain. First, we would like to have this setting to be theoretically motivated in some way, because it seems like we introduce functions that they have no theoretical explanation. Then we will also like to have an explanation for why dark energy would couple only to dark matter. So why isn't the coupling universal? And we will also like to motivate a form for C and D, otherwise we have many free parameters and also the functional form of the functions. So these questions were addressed in this paper here, where they proposed what's called the dark D-brane model. In this model, the universe is described by a compact higher dimensional spacetime, or a bulk, where we have embedded branes. Then what we consider is that our four-dimensional visible universe is described by what's called a visual brane, where the standard model particles and their interactions live. And then on the other hand, we have what's called the dark D brane, which is where everything that comprises the dark sector lives. So in this case, we will have dark matter and dark energy. Then we have gravity being the force propagating in the bulk. And so this means that in principle, if these two branes don't intersect each other, so if dark D brane is what we call a hidden brane, if there's no intersection, then they will be able to interact only through the force propagating in the bulk, so gravity in this case. Then we identify dark matter as the matter fields living on the dark D brane, and dark energy as the field that describes the motion in the extra dimensions of the dark D brane. Now, because of this setting, dark energy will no longer be just a canonical scalar field. We will have non-trivial kinetic terms that are introduced by the string theory setting that we consider here. And one interesting thing that happens in this model is that the induced metric on the brane is actually a realization of the disformal transformation. And it's also a particular realization of the disformal transformation that fixes the form of the function C and D to be dependent on this function H, which is called the warp factor that describes the geometry of the brane. So this means that this setting is able to address the three questions that I have just presented in the previous slide. By assuming that the dark sector can be seen as two distinct components that have a joint higher dimensional origin coming from the geometry and the dynamics of the dark D brane. In particular, these are encoded in the warp factor of the brane. And because they emerge in this way, we have an inevitable non-universal coupling. So it's not something we impose, it's something that arises from the setting. So dark energy interacts only with the matter fields in the dark D brane, which are the dark matter fields. Then this setting can be described by this action, also proposed in the same reference, where we see that we are in the Einstein frame. So we have the standard Einstein-Hilbert action for gravity given in terms of the gravitational metric G mu. Then we have the action for the motion of the de Bruijn in the extra dimensions. That will now be the action for our dark energy scalar field, which is now Dirac-Born-Infeld scalar field. We see that we have again an untrivial kinetic form for this dBi scalar field, which is different than the one we have for the canonical quintessence scalar field, but can be recovered if we take the non-relativistic limit of the dBi action. Then we have the action for the uncoupled matter fields. These live in the visible brane, and so they propagate according to the gravitational metric. And then we have now the action for the dark deep brane, or for the matter fields living in the dark deep brane, which is now written in terms of the induced metric on the brane, G mu tilde, and so meaning that whatever matter fields live in this brane will propagate according to this metric. Now, if we vary the action we have here, we see that this G mu tilde will depend on the scalar field phi, and so when we derive the equations of motion, we will have the usual terms coming from the dBi action and additional terms coming from this formal dark matter Lagrangian. And these terms will be encoded in what we see as a coupling function given by this. So all the terms would be the standard terms that we would obtain for a dBi scalar field, apart from the term that comes from the coupling, which is given by this. One interesting thing that we can immediately see is that there's no limit in which we recover the uncoupled scenario for the dBi scalar field. So since this was imposed directly, not imposed directly, but comes straight from the theory, we have no way of going back to an uncoupled case or even to a lambda CDM limit. In this case, we consider that the bulk is defined by an ADS5 throat with a quadratic potential, so given by a warp factor of this form and the quadratic potential of this form. Also in the original reference, they did a dynamical systems analysis from where they concluded that interesting scenarios arise when this parameter gamma naught, which is given by the product of the scales of the warp factor and the potential, is greater than 1, and we have a scaling solution that alleviates some of the conceptual problems of the lambda CDM model, for instance. So now if we study the model, what we find is that we have two different scenarios that are characterized by different limits of the initial values of the scalar field. So we find that the initial conditions actually play a significant role. So we can have, dependent on the initial value of the scalar field, positive couplings or negative couplings. We can also have the case in which the coupling might have been important in the past, but negligible in the present. So there's a lot of different dynamics in place. We see that, again, as we have seen for the quintessence scalar field, for the disformal quintessence scalar field, the coupling is only activated at later times. It's also activated later for higher values of gamma naught. So we see here for the higher value, it's activated later. And so just from this study, we expect that in principle, increasingly higher values of the parameter gamma naught will give us some sort of uncoupled or even lambda CDM limit, although not rigorously. Then if we go to the perturbations, we find that the background evolution also leaves a distinct imprint in the perturbations. We see that we have the effect from having different expansion rates according to redshift, and also different dynamical evolution for dark energy. We see that this dynamical evolution can lead either to a suppressor or enhancement on the growth of structures, depending on the dynamics. We also see when studying the perturbations that the perturbation of the coupling is scale dependent, and that's also imprinted in the perturbations. And we see that the deviations are more pronounced for models where the coupling is activated earlier and not for the ones where it's actually greater today. Now we wanted to take this one step further and also study the model in comparison with the recent data sets and see whether it can address problems such as the Hubble tension. So first we started by doing a data analysis just with the Planck 2018 likelihood using the class code interfaced with the Monte Carlo sampler Monty Python. We still have only preliminary results, but we can already draw some conclusions just from these. As I said before, we have no well-defined lambda CDM or uncoupled limit, and so it's hard to set out priors for the models, and therefore it's hard to have very tight constraints. These are the constraints we have so far on the parameters of the model, considering just the Planck 2018 likelihood. From the numerical analysis, we see that by using these initial conditions, we would expect to have a transfer of energy from dark energy to dark matter, and therefore to have a lower value for H0 when coming from CMB measurements. So this is exactly what we see. We had started by saying that there's a suggestion that models with new physics could be able to alleviate the H0 tension. However, the DBI dynamics only induces changes at late times in the evolution, and it has also been discussed the fact that models that only introduce changes at late times are not or are unlikely to be able to address the Hubble tension. Although we still have large error bars here, we see that in principle, although the models are compatible at 1 sigma, the values are compatible at 1 sigma, the best fit values for the dark DE1 are currently lower than the lambda CDM case. Even if they were the same, this would still mean that we don't address the tension in principle, because we would also expect to have a lower statistical evidence because we have additional parameters in the theory when compared with lambda CDM. Having said this, we also try to add background data such as BAO, Pantheon supernovae data, and cosmic chronometers measurements on the Hubble rate. And we also add the shoes prior on the magnitude of the supernovae. And these are the constraints we get on some of the parameters. So first, by comparing the H0 value and the gamma naught value, we see that we have apparently a degeneracy between the two, and this is also common, especially for CMB measurements, and we see the degeneracy is especially present for the Planck dataset only. Again, we see that the tension is still present. Here in the table, we see that the values, even when combined with the shoes prior on the magnitude of the supernovae, it's still quite low. And on top of this, we see that we have also very high best fit values for the S8 parameter. So we expect that the tension that exists with cosmic shear measurements would also be aggravated, because the lambda CDM value is also much higher than the one coming from cosmic shear measurements and has a best fit of around 0.834, whereas we see that all our dataset combinations have much higher values, and even though the error bars are quite big, we still wouldn't be able to reproduce the lambda CDM value at 1 sigma. So then, just to conclude, we have done a small review on these formal matter couplings, and we see that this allows us to encompass many generalized theories of gravity. And then we saw a specific theory that finds motivation in string compactifications. We saw that we have two distinct regimes, at least for the background, that is also imprinted in the perturbations given by the sign of the coupling. In principle, our numerical results show that we could find distinct observational imprints for the dark DE1 model, both in CMB and large-scale structures. But however, our data analysis shows that this model does not alleviate the cosmological tensions, and in principle also aggravates them. This is consistent with what has been discussed lately, that it is unlikely that changes to the late time expansion only can resolve the Hubble tension. And one thing we could in principle do would be to consider either different geometries for the warp factor or different potentials for the scalar field. So that's all I wanted to say. Thank you. If you have any questions, I'll be happy to take them.
Okay, thank you very much, Elsa, for this interesting
Thank
talk.
you.
And please share your screen.
Thank you.
Mm-hmm.
Okay, are there any questions? Anyway, people can also ask questions by with the chat, of course. Okay, so let's thank Elsa again for her talk.
Thank you.
Okay, and our next speaker will be Ezgi Kanay.
Hello.
Hello, and who will talk? Please share your screen. Okay. And the talk will be about simulation-wise comparison of Yukawa and Newtonian gravitational forces. Please go ahead.
Yes, can you see my screen?
Yes, we can see your screen, absolutely.
Thank you for the introduction. I'm Ezgi Canay from Istanbul Technical University. I'm a PhD candidate, and I would like to talk about our recent work with Maxime Eingorn today, which is about a comparison of Yukawa and Newtonian gravitational forces in a cubic cosmological simulation box. So first, I'll be briefly introducing our motivation. I'll be addressing, I'll be presenting the questions we'll be addressing, and then I will briefly talk about the cosmic screening approach because it is directly related to the Yukawa type gravitational interactions in a cosmological setting. This is how we obtain the Yukawa gravitational potential in a cosmological setting, actually. And then I will be presenting the analytical expressions for the Yukawa and Newtonian gravitational potential and force, both for periodic and free boundaries. Then, of course, we'll see how these four forces, periodic and plane Yukawa and Newtonian gravitational forces, behave in a cubic simulation box, cubic cosmological simulation box. And then we'll compare the periodic Yukawa and Newtonian forces, and eventually I will show how imposing periodic boundaries affects the plane Yukawa force in the simulation box again. And then I will briefly summarize our conclusions. So to begin with, the n-body codes for structure formation usually employ Newtonian approximation, which is relevant to nonlinear dynamics governing structure formation. But the problem here is that, of course, in the Newtonian approximation, relativistic effects that are an essential part of cosmological processes are disregarded. So we know that it is important in precision cosmology. So this can be overcome actually by employing the Yukawa gravitational potential in the equations of motion of these n-body codes. Why? Because Yukawa type interaction of gravitating bodies is relevant to all scales. By all scales, I mean both sub and super horizon distances. Because at small scales, the Yukawa potential is reduced to the Newtonian potential. But at a large scales, we have beyond the cutoff distance of Yukawa interactions, beyond the screening length, we see that gravitational interactions are significantly suppressed, and therefore the two laws of gravity deviate from one another. And this is in favor of the cosmological principle, actually, because we see that as we move to larger scales due to this exponential cutoff, we can say that the screening length of the Yukawa gravitational potential, and thus, of course, of the force, sets an upper bound for the sizes of individual cosmic structures. And the expressions for potential and force for Yukawa interactions follow directly from the Einstein equations. So we say that relativistic effects are inherent in the formulation here. So what we're interested in is how do the Yukawa and Newtonian gravitational forces for a delta-shaped non-relativistic source compare in a cubic cosmological simulation box, and we're interested in seeing how this difference is affected by the screening length, the interaction range of the Yukawa force. And then we would like to know at which physical distances from the gravitating body do we observe significant difference among the Yukawa gravity and Newtonian approximation. And finally, we'll be investigating the impact of periodicity in cosmological simulations, but only for the Yukawa force. So, as I said, I'll be briefly introducing the cosmic screening approach. It is formulated in General Relativity and the concordance lambda CDM model of cosmology. But the key feature in this approach is that non-relativistic matter is presented at discrete point-like particles, and the mass density is treated in a non-perturbative manner. And from the perturbed metric here, in which we introduced the first order scalar perturbation in agreement with the weak gravitational limit, we obtain the linearized Einstein equations, which give us a Helmholtz type equation for the scalar perturbation. That is why we get Yukawa type behavior for the gravitational potential and not Newtonian behavior. So we get a cutoff distance that we denote by this lambda effective, which is the effective screening length, which specifies, as I said, the cutoff distance of the gravitational interaction in a cosmological setting. The quantities with hats denote the shifted gravitational potential, so that we get this final Helmholtz type equation for the gravitational potential, which gives us the Yukawa behavior for gravity in a cosmological setting, of course. So actually, in a cosmological setting, the motivation for employing periodic boundaries is twofold, because contrary to what is suggested by concordance cosmology, the space may not be simply connected, but multiply connected. Which means it may have toroidal topology, and among the possible topologies, we also have the cubic torus. The space may be shaped as a cubic torus. And it is also suggested by observational cosmology, because cosmic microwave background anomalies in large angular scale observations, and in particular the quadrupole moment suppression, could be a consequence of special topology. And this could be attributed to the absence of long wavelengths in sufficiently compact spaces. And it is required that all three dimensions of such spaces are of the same order of magnitude, which brings us back to the cubic torus topology. And the size of such space is observationally bounded, is bounded by observational data, actually. However, it is also possible that periodicity is not required by topology, but still in cosmological simulations, periodic boundaries are often employed because in order to mimic gravitational interactions in an infinite universe, we need to replicate cubic boxes so that we have the proper setting. So in our case, in a space with cubic torus topology T cubed, and for a single gravitating body, a single particle M placed at the origin of coordinates, and for its periodic images, we have this Yukawa-Ewald potential with the analytical expression we have here. For the periodic potential, we employ Ewald summations because actually it is employed in n-body simulations based on Newtonian approximation, actually, because there we have a very slowly converging series for the potential, and in order to numerically manage this expression, they resort to Ewald summations. But for consistency, we also, the Yukawa potential and force already have good convergence properties, but to ensure consistency, we also employ Ewald summations in our potential and force expressions here. So as I said, for a single particle placed at the origin of coordinates, as well as its periodic images, infinitely many periodic images, we have this Yukawa-Ewald potential expression. The quantities with tilde in this slide and throughout the presentation are defined via these expressions here. L is our cubic torus period, also indicating the box size. And alpha is the free parameter of Ewald formulation. In our work, it is set to 2 because it provides a good balance between numerical accuracy and low computational cost. So similarly, we employ the Yukawa-Ewald force expression, but for the sake of simplicity and without loss of generality, we only employ the x component of the gravitational force in our analysis. And for an identical configuration, we have the Newton-Ewald potential, again for a single gravitating body at the origin of Cartesian coordinates, and for its images in all three directions. And similarly, the gravitational force, Newton-Ewald periodic gravitational force, only its x component here. Then later on, we will also be interested in the behavior of these forces for the free boundary problem. So now we have just a single particle, single gravitating source placed at the origin and no images. So we present our expressions for the Yukawa potential and force field, the rescaled quantities, and then here for the Newtonian potential and force. So then we have a look at the behavior of these four force curves, the periodic Newtonian and Yukawa forces, and Yukawa and Newtonian forces for free boundaries. We investigate their behavior for four different values of the screening length, lambda effective. The box size is set to unity, so when we take a look at the first two plots in the upper row, we see that for lambda effective equal to 0.05, the two laws of gravity, the Yukawa and Newtonian law of gravity, are significantly deviate from one another, except 2 points actually. The first is the immediate vicinity of the gravitating body, and the second is x tilde equals 0.5, which is halfway through the box size as we move further from the gravitating source. And since it is since the behavior of these forces is sensitive to the screening length, when we move to the second plot on the right hand side, still in the first row, we see that I mean, we see a similar behavior, but we'll see that the two forces, the Yukawa and Newtonian forces, behave like one another for within a wider region surrounding the gravitating source. The reason for this is the following. Lambda effective equals 0.05 and lambda effective equals 0.1 tells us that the screening length is very small compared to the box size. So we see that the cutoff distance of Yukawa gravity is very small. Therefore, as we move away from the gravitating source, we immediately get we immediately see that there is an exponential decay of interactions. Therefore, the Newtonian and Yukawa behavior immediately deviate from one another. That is why throughout this halfway through the box, we see that the two laws of gravity do significantly visibly deviate from one another. But when we move to the lower row here, when the screening length is equal to the box size and equal to when it's twice as much as the box size, instead we see the two laws of gravity behave similarly throughout the halfway through the box, but it's now the periodic and plane forces that are deviated from one another instead. The reason for this is that we don't see the distinction between the Newtonian and Yukawa forces here, because the interaction range of the Yukawa force is okay. yeah, the interaction range of the Yukawa forces is large enough so that we don't see the exponential decay immediately. So for a wider region surrounding the gravitating body, we have the similar behavior of the two laws of gravity. But here, the distinction between the periodic forces and the plane forces becomes clear as we move to x tilde equals 0.5, because the periodic forces tend to 0 here. However, again, due to the large interaction range of the Yukawa force, we still have non-zero force as we move to x tilde equals 0.5. Then, based on this study, we zoomed into the regions where this relative error associated with periodic Newton and Yukawa forces becomes significant in the box. And we immediately see that for tilde lambda equals 0.05, the 1% error is already encountered at about 1% of the box size. And again, as we move to larger lambda effective, these points of fixed percentage errors are shifted away from the gravitating source as expected. And switching to the physical setting, we set the physical size of the simulation box to 1.3 gigaparsecs today for zero redshift. And we saw that this 1% error is encountered at 530 megaparsecs, and a relative error of 10 to the minus 5 is encountered at 12 megaparsecs, which is very close to the gravitating source. And as we move back to the epochs, back in a matter-dominated epoch, we see that the positions of the percentage errors are shifted towards the gravitating body, so the situation is more drastic back there. And we studied also the differences between periodic and plane Yukawa forces, and we marked the positions of fixed percent errors in the box, and we saw that contrarily for larger screening length, the locations of the percentage errors are instead shifted towards the gravitating source here. And again, for the physical size of when the physical size of the box is set to 1.3 gigaparsecs today, we found that 1% error is encountered at 173 megaparsecs, and this goes as low as 18 megaparsecs for 10 to the minus 5, for a relative error of 10 to the minus 5. So we have realized that in the cubic cosmological simulation box, as I just said, a relative error of 10 to the minus 5 in comparison of the periodic Newton and Yukawa forces takes place at less than 1% of the box size from the gravitating source. And at earlier epochs during the matter domination, the locations of these fixed percentage errors are shifted towards the gravitating body. So it is more significant as we move, it gets more significant as we move back in time. And for plane and periodic Newtonian forces, a similar investigation was carried out, and an error of 10 to the minus 5 was reported to take place at 1% of the box size. But here we have shown that the situation with respect to the relative error associated with different laws of gravitation is actually more significant. And again, in comparison of plane and periodic Yukawa forces, the 10 to the minus 5 relative error takes place at 18 megaparsecs from the source today, but the locations of these percentage errors do not change as much as they do in the case of periodic Yukawa and Newtonian forces. So that's pretty much what I wanted to say. Thank you for listening. If you have any questions, I'd be happy to answer.
Okay, thank you very much, Özge, for this interesting talk. And please share your screen.
Okay.
Okay, thank you. Thank you very much. Are there any questions? Okay. If not, this concludes actually this afternoon session. Okay. The session will resume tomorrow at 9:30. And I don't know, maybe somebody want to ask a question concerning all the talks. I mean, concerning any talk. Okay, if not, let's thank all speakers. Okay, Levon, you wanted to ask a question?
No, I just wanted to say good. I mean,
Okay.
show my face when I say goodbye.
Okay, so let's thank all speakers again for this very interesting afternoon session, and see you tomorrow. Okay. Bye-bye. Bye-bye.